Lecture number 11 related to out of autoclave processing. And so far, we have mostly been talking about the standard ways of processing composites, which most of them use what is called application of pressure due to the gas in the oven, which is in short, it is called autoclave process. But what is happening is that you will observe that more and more components are being made that are larger than the autoclave. So even though the autoclave pressure is only approximately 100 to 125 psi, so just imagine the amount of volume that you need to take up in the autoclave. So from a manufacturing perspective, these equipments are in the multi-million dollar range, multi hundreds of million dollar range, and the amount of area that needs to be taken up for these manufacturing places are also unbelievably large. So what people are trying to do is to reduce the cost and to manufacture things fast. So an autoclave run can probably take a couple of days. Even though the actual run might be only like overnight or 20 hours or whatever, but by the time you heat it up and cool it down, it is going to be a couple of days. And after that, you need to take it out. Then you need to strip off the composite. You need the part. Then you need to clean it out and things like that. It is going to take forever. So expensive, and you do not know what you're going to get sometimes. So what people are trying to do is to make components using an out of autoclave processing. So this is very comfortable, very useful for making really large shapes and large components. Okay. So this actually came out of a guest lecture that was given by one of our colleagues here in Tulsa, and they used to be called American Composites Group. Then they were taken over by another company, and then they were taken over by Cytec, which makes the carbon fiber prepreg, and now they are part of the Solvay Group, which is a chemical group, and they supply a lot of chemicals for the composites industry. So they are owned by Solvay, and they are right here in Tulsa, and they make these prepreg that can be used for out of autoclave processing. So what are the benefits of, as I mentioned to you, larger parts with fewer subcomponents and joints can be made, and it removes, the most important thing is that it removes the constraints on shape. Autoclaves are expensive cylindrical pressure vessels, and it significantly increases the available subcontractor base and encourages competition. So it is less expensive compared to the uh, parts that are made by autoclaves. I do not know. I think this was an autoclave in the ACG group, or I don't know if they are showing the autoclave on the NORDAM facilities. I'm not really sure. But I was told that this is an autoclave. This is the picture of an autoclave right here in Tulsa. So a couple of years ago, maybe like 10, 11 years ago, the Air Force started a process, especially when they were thinking about making the F-35s using about 40 to 50% composite parts. They said that if you have to reduce the risk for affordable structures, especially affordable composite structures, then you need to make them all in one piece. Large integrated structures, bonded structures, and most importantly, you need to reduce the part and fastener count. So it reduces the direct and indirect cost of components. So if you can remove the size and geometry constraint that is due to the autoclave size and shape, then you can make large parts and you can use a relatively inexpensive equipment such as an oven. For example, we work with a startup company here in town called Infinite Composites, and we are making about 20-foot long by about um, 2 to 3 feet in diameter composite pressure vessels. In the past, they could only be made using an autoclave. What we did was we just put a furnace around the part after it was made, and it was literally the outside walls were made out of cardboard. The inside was um, well insulated, so whatever temperature it went to, it did not burn off uh, the cardboard walls of the furnace. And if you have to redo the furnace, you could do it. And then it helps to reduce the tooling costs, and it because the out of autoclave system possesses low temperature cure capability. Okay, and then you can reduce the need for what is called the core stabilization. So it again reduces, goes to the point of reducing cost. So I'm not going to go over every single slide in this presentation, but I will quickly go through that. I would like you to go through this presentation, and this is pretty self-explanatory. Okay, so what is the, so I talked about what are the advantages, and next we will talk about what are the materials. So you can use low cost oven and vacuum bag processing, but the most important requirement is that the pre-preg has to be breathable, and how you put it together is very critical. And then when you are heating it up, the resin has to flow and evenly wet out the fabric. So viscosity during the cure cycle is critical. It must remain high enough so that it doesn't flow down, flow out, and the material and the matrix remains in the within the part, but it needs to be breathable also so that there are no porosity and things like that left behind. By the way, why do people typically use autoclaves? It's because you want to avoid porosity in the part as much as possible. So when you make it using an out of autoclave process also, you have to make sure that the porosity is minimized, and it is within the requirements of the part. And then the other advantage is that you could use what is called, um, you can use this matrix as a film. So you place it or drape it over the fabric, and during the heating process, during the heating and vacuum bagging process, that uh, that matrix will melt and infuse into the autoclave pre-preg. So that is also another reason why the pre-preg has to be breathable. And the out of autoclave process is already being used very widely for marine and aerospace prototyping since the 1990s. And the performance, so what is the requirement of out of autoclave processing? The material that we use has to result, maybe not the same as 100% of what you would get with an autoclave process, but at least it should be 90 to 95%. It cannot be like 65 to 50%. It has to be about 90 to 95% of what you get in an autoclave process. So these are being used in a number of industries, and you can use all kinds of processes, the standard composite processes. It can be wet layup, it can be liquid resin infusion, it can be resin film infusion, and prepregs. So uh, what you would like to do is to use prepregs as far as possible. And why prepregs? Because prepregs are more standard. You do not have to worry about the quality of the prepreg because somebody else is making it and giving it to you. So you can use the prepregs as a autoclave process more than any other type of process. But the resin film infusion is, or RFI, is also another technique that autoclave processing has been using quite a lot. So in the liquid resin infusion process, there are three varieties of that: RTM, Wartum, and it is another process called squirtum. I think I will remember the definition of squirtum in another um, in the next. Let me check that. I will tell you what it is. I want to remember that. SQRTM. Hmm. It does not tell me that exactly. So maybe that is another thing that you could probably uh, look through. Yeah, it is called same qualified resin transfer molding. I don't know why they call it same transferred. It's a closed mold composites manufacturing process similar to RTM, and same qualified means you are injecting the same resin as that used in the prepreg layup. So, which means that uh, you can use the same resin as in the prepreg. So you're using a prepreg for using the RTM process. So that's why it's called squirtum. I'm glad I looked it up. So that's something that I learned today. I had remembered, but I had seen that earlier, but I had forgotten what it was. So thank you for making me do that. So um, the pre-preg, there are a couple of different things that you need to know. First is that you can either have a 350F pre-preg or a 250F pre-preg. So the American Composites Group qualifies it as HTM technology, or high temperature materials technology, and 250 is it's called the medium temperature manufacturing technology. And then there is a these also need to be post cured at a load, post cured afterwards. So whether or not you are using post cure, um, you can call it differently. And then there is also another set of prepregs that are low temperature molding technology. So the low temperature, the advantage is that you can use low cost tooling, and it can, suppose you are making the first prototype, you could use the LTM material. They also have the variable temperature molding, so it can be anywhere from 150 to 250F. So one thing to note here is that if you are using a 250F, you will cure it for a shorter time. If you are using 150, you have to cure it for a longer time. So they have these different prepreg series, and these are all signified by, like, in this case, it can have high viscosity, low flow, or intermediate viscosity, or low viscosity for heavyweight reinforcements, etc. And the advantage is that many of these systems are co-curable, and they are also variable cure capabilities. So you can have 16 hours at 149 degrees F, and then you would post cure it at 190 degrees F, or you would do 16 hours at 149, and then you would do post cure at 260 degrees F. And if you are using these components at room temperature, then you don't need to do post cure. And one thing to note is this: many of these pre-preg, even if you keep it in the freezer, they would only last for 6 months. And if you take it out from the freezer for cutting and things like that, then the out life is less than 30 days. So these are some of the marine applications. So they are like high performance yards, interiors, like, hull structures, and the components that are high up and things like that. I mean, they could be wine luster based materials. So the advantage is that, I mean, you would cure it at 65 degrees centigrade or 150 F, and the advantage is that it allows the use of low cost tooling. Again, in the infrastructure, you would use them for making wind turbines, mass transit systems, and again, the material needs are similar to those of marine applications. Um, or, if you are making them on site, you could use that. So, you cannot make it and take it inside a furnace. You have to cure it outside. So if you needed to heat it up, how would you heat it up? Think about it. What you have to do is you have to use heating jackets, and the heating jackets are heated up and it goes to a certain temperature. So you can't go to very, very high temperature. So you could probably go to, say, maybe like maximum like, 120, 150 degrees F, or maximum 250 F, not more, because your tooling has to transfer that heat inside to the component. So if your tooling is very, very thick, then you cannot really heat it up a whole lot. So you can make the components on site using out of autoclave. Or, if you are doing infrastructure, like, bridge repair, in civil engineering repairs, or, if you are doing heritage buildings, um, you are repairing them. So the advantage is that you can do low temperature in situ out of autoclave cure. So use a lower temperature cure, and then once it is done, it is as good as new. So if you repair that, then what are the advantages? It increases the load bearing capacity, and you can make very, very innovative architectural designs, and it is very ideal for certain scenarios. So marine infrastructure, it uses low cost resins, like, wine lusters or polyesters, and low cost resins, and glass fibers are e-glass almost extensively. For aerospace, you have to use you have to use a higher temperature cure, and so it could be graphite epoxy, and those need to be uh, heated using solar heating. So you would focus the heat, sun's rays, onto the prepreg in order to cure it. So again, these are some examples of um, where composites are made using out of autoclave. So here um, is the solar planes that were completely made in one single piece. Um, and then I believe this was made by a company out in California, probably Virgin Galactica. And then this one is made by, I believe it is made by Lockheed Martin at their Palmdale facilities. It's a UCAV, unmanned combat air vehicle. Okay, so this one is X-36 plane. So these are all made using out of autoclave processing. So here is an example of cost savings achieved using the first generation is low temperature curing at 60 degrees centigrade. So they have figured out that you're saving, the cost itself is 70% in the tooling, and uh, design and development is 23%. So it gets down to this much. Almost tooling cost reduction is 70% and part cost reduction is 50% using this approach. So this is the Delta launcher fairings, and they are made using low temperature out of autoclave pre-preg. So what are the um, issues that we need to worry about? You need to worry about porosity, toughness, how much life do you get when you take it out of the freezer, what is the cost, and what is the handleability of these materials. So you can see that this is the standard material properties, and if you increase the temperature, increase the temperature to which these are exposed to, the standard material, it has a reduction from it's a compression strength after impact versus wet TG for various pre-preg epoxy resin systems. So this is the autoclave curing system, and this is the out of autoclave capable system. So what you can see is that the out of autoclave system is even better than the autoclave curing system, even after exposing to wet conditions and higher temperatures. Again, you can see that these properties are almost the same as the pre-preg system. So you can see that just because you use out of autoclave pre-preg doesn't mean that you're going to have any kind of property degradations compared to the traditional materials. So here again, there are some properties that are listed here. I'm sorry, this is a very busy table, but you can see that these properties are pretty good. And so what is the advantage? So you can keep them out for 10 to 12 days and 30 days out life. And in this case it is 21 days. This could be less than 30 days, and it's about 15-20 days stack life, 35 to 40 days out of life, out life. So all you have to do is, as long as you are ensuring that you're using it within the time limitation, you should be able to get the right kind of properties. So these have been qualified and is being used by a number of manufacturers, like in this case Airbus. So you can see that and they are qualified. So, in this case, it is the Airbus wing spar, and in this case, it's a trailing edge. So, these were made using out of autoclave prepreg type of material. So, this was a demonstrator for Saab and Fokker, and so these are made using these materials, and it is made outside. So this was a demonstration part, but what they found is that it was able to, I mean, it would have the same kind of properties as the parts made using standard prepreg materials that are autoclaved. So once you take it out of the autoclave, you have to make sure that it reaches a room temperature, and then any remaining moisture is removed by paper towel before you do the layup and curing. So these are the steps in the manufacturing process. So again, these are the different medium temperature prepregs. So they were qualified by Airbus, and so this one again, I mean, I was telling you about uh, space. I'm sorry. This is made by a company called Space Composites. Uh, just a minute. Let me tell you who is the guy. I mean, I think um, I should have remembered. I'm sorry. Uh, Space Composites. No. Hmm. Who made the first solar um, composite plane? Hmm. No, that's not the one. Sorry, I'll come back to it in a while, in just a few minutes.